In this video, we're going to talk about graphs of special polar equations. So this is the first of a kind of a two-part video. Today we're going to look at, or in this video, we're going to look at three different types of graphs that come with polar equations. And in the next video, we'll look at three more different types of graphs. So we're going to start with this one. We've got r equals sine of theta. And so what we're going to do is we're going to start by just plugging in different theta values. I have a table set up here, and I'm going to plug in sine of 0. And so you can use a calculator, or if you know your unit circle, you know that the sine is the y value on the unit circle. And so at 0 degrees, that's just 0. And then at 30 degrees, we know that the sine is 1/2, so 0.5. And in an effort not to sit here and drone on about how to plug things into a calculator, we get all of these other values. So I've got my table already pre-filled in, and then I'm going to go graph these points. And so I'm going to graph 0, grab a pen, 0, 0. I'm going to graph 30.5. And so I think what I'm going to do actually is I'm going to make 1, 2, 3. I'm going to make 4 lines be 1. So 0.5 is going to be 2 units out. So right there. And then we've got 45 will be 0.71. So if this is 0.75 here, it's going to be right before the third circle. So there's 45.71. And then 60 is going to be 0.87. It's going to be somewhere out here. And then 90 is going to be 1. And trust me, it's not going to take too much longer. 120 is going to be 0.87. Right around there. 135 is going to be 0.71. 150 is 1/2. And 180 is 0. And then if you notice, as we graph the next point, 210 negative 0.5. So 210 is right here. And negative 0.5 will get us right back to the second dot that we plotted. And so there's just going to be a lot of overlap. Basically, everything here down is a repeat value. So we're not even going to bother graphing all those. And so what we get, if I can draw a nice one here. Shucks, that was good for a little while. We're going to get a circle. So this ends up being a circle in polar coordinates. So the first example of a special graph is going to be a circle, and it's going to be like r equals sine theta is one example of a circle. So let's look at the next example. We'll kind of come up with what a circle equation looks like in a moment here. So we've got r equals 4 cosine theta. So with this one, I've got another table set up, and I'm going to plug values in. I know at 0, cosine of 0 is going to be 1, and then I multiply by 4, so this is going to be 4. And then if I fill in the rest of them here, excuse me, I need to fill in the 30-degree one. So the cosine at 30 degrees is going to be root 3 over 2 times 4. So root 3 over 2 times 4, which is going to be 0.3 or 3.5, excuse me. That's about 3.5. Then I got the rest of them filled in as well. So I'm going to graph these. At 0 degrees, I'm out 4. And this time I'm going to use each circle is 1 unit. So 1, 2, 3, 4. There we go. And then at 30, we're at 3.5. And then at 45, we're at 2.8. At 60, we're at 2. At 90, we're at 0. At 120, we're at negative 2. So here's 120. We go to the other direction. We're going to be right there. At 135, we're at negative 2.8. And at 150, we're at negative 3.5. And then at 180, we're at negative 4, which is back to that first point that we graphed. So this, once again, is going to be a circle as well. Let's see if I can graph this. Not too shabby. So this is also a circle. So a circle equation is going to be in this form. R equals K cos theta or r equals k sine theta. And if you notice the one off on the poles, like on the east and west, that's going to be cosine. So we can say this is east and west. What I mean by that is it's going to be sitting on like the 0, 180 line. And then if it's on the north-south line like this, that's the sine circle equations. Okay, so there's our first of our 3 special equations. Let's look at the next example, example 3. So now we have a situation set up where it's r equals 3 cosine of 2 theta. So this is going to be a pretty big table to fill in. And these are kind of tedious, as you can probably tell. So they're going to take a little bit of time as you do them. But the procedure is pretty much the same. And this time I'm actually going to use the graphing calculator to help me out. And so what I'm going to do is I'm going to turn on my graphing calculator. I've already got it kind of set up, so I was doing some prep work here. So let me show you how we get this set up. We're going to start by hitting mode. And then the normal way we set this up is function, but I want it in polar mode because we're working with polar coordinates. I'm going to switch this over to polar. And then I'm dealing with degrees in this one, so I'm going to switch it over to degrees. And then what I do is if I click y equals, I've got some polar equations I can type in. So I'm going to do 3 times cosine of 2 theta. And theta is just like the X button on a graphing calculator. It automatically selects the correct letter, depending on what mode you're in. And so what I'm going to do is I'm going to use the calculator to give me the table, and then I can graph from there. So I'm going to hit second table set, and it looks like I'm starting at 0 degrees, so I'm going to start at 0. And then I'm going to change my delta table, and it looks like I'm going up by 15 degrees each time. So I'm going to say 15. And the reason I chose 15 is because of this right here, this 2 theta. I'm always going to be doubling my angle. So when I type in 15 for theta, it's really 2 times 15, so it's really 30. When I type in 30, it's 2 times 30, which is 60. So I want to pick something like 15-degree increments to get more of what's happening with this graph. That's why I chose to go up by 15. So you could go up by, you know, 10s or something. That might be a little bit weird, but 15s will work just fine. Okay, so back to our calculator. We've got our table set up. Now, if we want to look at the table, I'm going to hit second, graph, and there's my table already set up for me. So I've got 0, 3, 15, 2.6, and so on. So let's type those in. 0 is going to be 0, 3. 15 is going to be 2.6. And then I think I have this all set up here. There we go. So there's the rest of them. And then I'm just going to start graphing. So I go 0, grab my pen here, 0, 3. So there's going to be 0, 3. 15 is 2.6. 30 is 1.5. 45 is 0. 60 is going to be negative 1.5. So we're going to be over here. 75 is negative 2.6. And once again, I'm going to speed this up a little bit here. 90 is negative 3. And I think I have the rest of them plotted. Let me click on them and show you here. There we go. So I've got all of these points plotted. And you just go in order in which you graph them. So we started here. We're going to go like so. Oh, I think I got off a little bit here. Let me fix this. Messed up on one. So this was 1.5. This was 2.6. There we go. All right. And then we go around here. And we connect the dots. And look at that. It's a pretty flower, isn't it? So hopefully yours looks a little less squiggly than mine. You'd swear I was on some caffeine rush right now. Anyway, this thing is called a rose curve, which somewhat makes sense. If the mathematicians who named this knew their plants, they would probably call this a daisy curve because it looks more like a daisy than a rose. But I think because of the petals, they wanted to name it after a flower. And so what we're going to do is we're going to start fresh here in Desmos, and I'll show you how I got to that point. And so we're going to look at a rose curve. And so what I'm going to do is I'm going to go up here to graph settings in Desmos just to kind of show you how this works. And then over here in the grid, this is a polar grid. So now I can be graphing in polar. This is kind of the nice thing about Desmos. And then I can type in my equation, R equals 3 cosine of 2, let's do this, 2 theta. Theta, I'll do that. So this is the rose curve that we just looked at. That's exactly what we graphed. If you notice a couple things, one here, this rose petal or this flower petal thing, from the center to the outside is 3, and that probably comes from this 3 in our equation. And then the 2 does something as well. So what I'm going to do is I'm going to look at what if I change some of these numbers. So if I change this 3 to, let's say, a 4, then the petals are going to be 4 wide. So that's kind of what I was just saying. That's probably what you had predicted. Let's say I change this 2 to, well, if it's 1, then it's just a circle like we looked at before. What if I change it to a 3? So if I change it to a 3, it's got 3 petals. If it's a 2, it's got 4 petals. All right, what about if it's a 4? What do you think is going to happen? I'll put in 4 there. It looks like if we put 4 there, we get 8 petals. What if I put in 5? 5, we get 5 petals. So 6, we get 12 petals. And hopefully you're starting to notice a little bit of a pattern here with these rose curves. With 7, we get 7 petals. With 8, we'll get 16 petals. Okay, let's head back to what we were doing and write down a few things about rose curves. So rose curves follow these forms. R equals A times sine of B times theta, or cosine. And if it's even, there are how many petals? So if this is an even, if B is even, so if the number on the inside is even, then there are 2B petals. It's always double what that number is what we noticed in that pattern. If it's odd, then it's not double, it's just that number. So if it's 3, there's 3 petals. It's 5, 5 petals. And then the length of the petals that we just talked about, that is A units long. So these are called rose curves. They follow this, this equation, and we just kind of looked at what each of those A and B do. All right, so to finish it out, we've got one more. And it looks something like this. And so there's no sine, there's no cosine. It's just R equals some number times theta. And this always has to be in radians. So if you use your calculator to make a table and you put it in degrees, you're going to be way off. So we got to change that to radians. So let me grab my calculator here. I'll turn it back on. We'll go to y equals, and it's 0.5 times theta is the equation here. So then when I go to table set, I don't want it to go up by 15 because we're not dealing with degrees any longer. I want it to go up by, well, I'm going up by pi over 6 here. So I'm going to do that. I'm going to say pi divided by 6. Now, some of you might be wondering, well, do I have to switch my mode here to radians? No, because we're not doing sine, cosine, tangent, anything like that with our calculator. We're just doing 0.5 times that radian measure. So it's not needed. You can, it's not going to hurt anything, but it's not needed in this situation. So if I hit second graph and look at the table, I've got my table already set up there for me. So I think I have this set up. Do I need to enter any? No, it's all set up for me. And so if I graph a couple of these points, we've got pi over 6 is 0.26. So pi over 6 is 0.26. We're going to be like down here. And then we've got pi over 3 is 0.52. That's going to be somewhere around here. Pi over 2 is 0.79. So we're going to be like somewhere over there. And then I think I have all the rest of the points plotted. So let's see. There they are. So this ends up being kind of a cool little spiral here. Looks almost like one of those seashells or snail shells or whatever those are. So this does turn into a spiral because every time theta gets bigger, we're multiplying by 0.5. And so as the radian measure is getting larger, we're getting farther away from the center. And so we're going to have this spiral here if we connect all these dots. And it's just going to keep going on. I stopped here, but it is going to keep getting bigger and bigger. I don't know where it's going to, go over here. So I should maybe, it's probably wrong, but it's going to keep going on. And it's going to keep spiraling and spiraling. And so if we go back to Desmos, and oops, that's not what I wanted. Let's see, Desmos, there we go. And I type this in. I've got 0.5 times theta. Oops, I forgot the 5 there. There's our spiral of Archimedes. This is called the spiral of Archimedes. If I change that 0.5 to a 1, it's not quite as dense. If I do 0.2, it's going to be a lot more spirally. I don't know if that's the right word. If I change this to like a 3, it's going to get bigger really rapidly. So that number out in front definitely affects how fast this thing is moving. So this is called a spiral of Archimedes, and these are always in the form r equals k times theta. And as k gets larger, the spiral expands out more rapidly. So anything in this form in polar coordinates is going to look like a spiral named after the great mathematician Archimedes. It's called the spiral of Archimedes. All right, so that ends the marathon of part 1. Part 2, we'll be talking about 3 other special polar graphs.